In this video, we're going to be talking about series. This is kind of the first of, many lessons on series that we'll cover in Calculus BC. Today, we're going to be talking specifically about, just series in general, their convergence and divergence. We'll talk about the geometric series, and we will also talk about the telescoping series, which is one that is probably unlikely to show up on the AP exam, but it makes use of something we did a couple units ago. And it's a nice series to look at, especially when you start to think about convergence. Okay, so anytime you want to talk about series, you got to start with sequences. And really, before I get into it, I will say that I am presuming that you know a little bit about series, that you've seen the sigma notation before. This was something that we did last year in pre-cal, but if you were not in my pre-cal, you may not have seen this before. But the thing is that in this course, it's really it's not such an issue of the notation. It's about the concepts, really. It really is about the concepts. So 1, 2, 4, 9, 16, 25 is a sequence of numbers, right? It's really just a function with domain natural numbers rather than real numbers. And so we can write down an expression or a rule for this. What is going on? What's the deal with 1, 2, 4, 9, 16, and 25? Squaring. Okay, you're squaring 1, you're squaring... Wait. Oh, there's one. Yeah, there's one in here that does not belong, right? Oh, man. Oh, goodness. I probably could re-record this video, but I think I'm just going to stick with it. Okay, 1, 4, 9, 16, 25 is a sequence of squares. Okay, and this is where we say a sub n, so the nth term of sequence A is given by n squared. Okay, so we can write a little rule for that. Last year, or maybe in a previous course you took, you may have written recursive rules for sequences. The next term is given by the last term plus something or times something or done something to it. We won't need to deal with that in this course. And so we're mostly just looking for an explicit formula for the terms of a sequence, the terms of a series. And a series is something that we're going to form by adding together the terms of a sequence. Okay, so 1 plus 4 plus 9 is the first 3 terms of that sequence we were just talking about, a sub n equals n squared, added together. So what we do is we say that this is the sum, wrong color. The sum, so that means sigma for sum, from n equals 1 up to 3 of n squared. Okay, so you plug in n equals 1, that's 1. You plug in n equals 2, that's 4. You plug in n equals 3, that's 9. You're adding them together. That's where the sigma comes in. That's how you write that. Okay. This over here, 1, 4, 9, 16, 25, 36, plus dot, dot, dot. Now the plus dot, dot, dot indicates that that's just going to keep going on forever. That is something that we could say, all right, the sum starting from 1 going up to infinity of n squared. Now, what do y'all think is going to happen if we keep adding up larger and larger squares? What's going to happen to the total sum? Yes, it's going to approach infinity. Somebody said it was going to diverge, and that's nice language. I don't know. Maybe we talked about this last year, and we said that if it went to infinity, we'd say it diverged. Specifically because we're just adding bigger and bigger numbers, so the sum is just going to grow really large. I'll have more to say about this in a second. And before we start talking about convergence, divergence, the causes of these things, we do need another kind of piece of terminology that they will use from time to time, and they'll talk about the nth partial sum of an infinite series. Okay, well, the nth partial sum is where you add up the first n terms. Okay, so if the one up above, that where we had 3, we would say that that was the third partial sum of the infinite series 1 to infinity n squared, k squared, whatever you want to call it. Sometimes the index is k, sometimes it's n. I have seen on College Board items them use j or even I. I try to avoid I for various reasons, so I'm mainly going to use n and k in these videos for the index. So for example, I'll start with the partial sums of the sum from 1 to infinity of 1 over 2 to the n. Okay, well, the sum from 1 to infinity of 1 over 2 to the n is going to be 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. The first partial sum is just going to be 1/2, right? You just add one of them together, and that's not really very interesting. So what I'm going to do is I'm going to start with the third partial sum, S3. Well, that's 1/2 plus 1/4 plus 1/8. And that's going to be 7/8. The fourth partial sum will be 1/2 plus 1/4 plus 1/8 plus 1/16, which would be 15/16. And the fifth partial sum is going to be, 1/2, 1/4, 1/8, 1/16, and 1/32. Which is going to be 31 over 32. Okay, so we can start to see a pattern emerging. I need some more room, and I'm going to say that the nth partial sum is going to be okay. The denominator is always 2 to the n. We see 2 to the 3 in the denominator, 2 to the 4 in the denominator, 2 to the 5 in the denominator. And then the number above it is always just 1 less, so it seems to be 2 to the n minus 1. Now, I'm going to scroll down a little bit, and I'm going to say that the series converges if the limit of the nth partial sum exists as n goes to infinity. And if it does exist, that's the value the sum is going to converge to as you add up an infinite number of terms. And in the same way, we'll say that this sum diverges if the limit doesn't exist. And this does not only mean that the sum goes to infinity. I will kind of come up with, I've got an example for you that diverges despite not going to infinity. And I think it'll make a lot of sense to you. So before I move on, it might be good to figure out what the actual value of this infinite sum is, right? We might want to take the limit of this nth partial sum. So let's take that limit. Limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. Well, you can see that the sums are getting closer and closer to 1. You could look at it as the top and bottom are essentially the same. The relative growth rates are the same. Or you could even divide 2 to the n over 2 to the n, which would be 1 minus 1 over 2 to the n. 1 over 2 to the n is going to go to 0 as n goes to infinity. But either way, this limit is equal to 1. Okay, so we say that this sum converges to 1. And I'll have more to say about this when we talk about geometric series. All right, next we've got a fact about convergent series that will actually generate us a rule to find out a quick way to tell if a series for sure diverges. Okay, so if the sum converges, then the limit of the terms has to be 0. And if you think about that, there's no other way for you to, add up an infinite number of things and have it converge to something unless, the farther out you go, the more you're just basically adding nothing. So that's, and the more you think about it, that should make a lot of sense. This is something that we can prove. Okay, so I'm going to say, okay, I'm going to assume the sum converges. Suppose it converges to L. So the sum from 1 to infinity of a sub n is equal to L. By our definition of a convergent series, that means the limit of the partial sums, oops, I need a limit there, is equal to L. But we know that we can get the nth partial sum by taking the last partial sum before that and just adding the next term. And that's what we're going to show goes to 0. Okay. So what I'm going to do is I'm going to make that substitution on Sn right here. So this means that the limit of S sub n minus 1 plus a sub n is equal to L. Now, we've got a limit property that we probably haven't even thought of for a really long time, but we can split this up into two separate limits. Plus the limit of an, the limit of the terms, that's still equal to L. Just using that property of limits. Now, the limit as n goes to infinity of S sub n minus 1 is going to be the same as the limit as n goes to infinity of S sub n. Right? N is going to go to infinity, and as n gets really large, you subtract 1, it's still really large. So I'm just going to say I'm also thinking that the limit as n goes to infinity of S n minus 1 is equal to L. So I'm going to actually, make that replacement. So that means that L plus the limit of the terms is equal to L, which means, like I had set out to show, that the limit of the terms must be 0, right? So that one's just a nice kind of proof of that that's right at Chell's level. And this will be what we call the nth term test for divergence. And really what this is this is going to be the contrapositive of the previous theorem. Okay? If the terms of a sequence don't go to 0, what do you think would necessarily happen? Yeah, it's gonna grow. It's gonna diverge. Okay, so I would say rather than just saying the series must diverge, maybe a better way to think about it is the series doesn't have a chance to converge. And I'll say that again for you to kind of think over this statement in your mind. If the individual things that we're adding together don't go towards 0, the series doesn't really have a chance of converging to one particular number. And, it's probably fine, the series adding together the terms of the sequence, but I'm actually going to change that to the terms of a series. That's what I meant to say. So for example, I'm just going to throw 4 series at you and say which of these definitely diverge and which kind of have a chance of converging. Okay. So what you want to do is you want to take the limit of the terms. Notice how for these 4 examples, all 4 of them have a kind of a different starting value. And the point I'm trying to make there is that it doesn't matter as far as the nth term test, because the nth term test is you take the limit of the terms as n goes to infinity. You analyze that, so it doesn't matter where you start. You do that analysis. You determine definitely diverges or possibly, potentially converges. Okay, so let's just start off with, I'll do one of them, then I'll let you all kind of think about the others. Okay, so let's take the limit as n goes to infinity of 2 to the n over n to the 3. Well, 2 to the n is exponential. And that's going to grow faster than any polynomial. Basically, if you think about L'Hopital's rule, now I know that 2 to the n is a thing that y'all might have a little bit of difficulty taking the derivative of. But really, that's e to the log 2 times n. And exponential functions are at least related to their own derivatives by some sort of constant. And you keep taking that derivative, and you're going to keep getting the 2 to the n. Now, you'll have some other numbers on the outside. But after, I think, 3 times of taking the derivative on top and bottom, that n to the third will go to a constant. And as n goes to infinity, you still got that 2 to the n on top, and this is going to infinity. Okay, so this goes to infinity, doesn't exist, definitely diverges. Now, I'm going to freeze the screen for those of y'all in here, and I'm going to pause the video for those of y'all watching at home, and I want you to not even really, you don't have to work this out on a sheet of paper or anything, just think about the next 3, think about the limit of the terms as n goes to infinity, and think about what conclusion am I supposed to draw from that. So yeah, if you're watching at home, you definitely want to pause the video right now, because the answers are just right about to pop up. Okay. So if you look at these, you've got 4 series, and these are just series of numbers, and that's going to be our 11th unit in this course. We're just going to look at series of constants, adding a bunch of numbers together. Then in the unit after that, we're going to look at series, basically looking at polynomials as series. And it turns out that you can model all of the functions that y'all are familiar with using an infinite degree polynomial. And also, this has, the study of Taylor series is incredibly applicable to, modern stuff, because polynomials are just multiplying and adding numbers. And we know something else that likes to multiply and add numbers. Computers like to multiply and add numbers. So, and this is how your calculator, gives you the value of sine, or even e to the x. It just uses a polynomial to calculate that. And it turns out you don't even need that many terms of a polynomial to get a really accurate estimate of sine, cosine, tangent, e to the x, log even, things like that. Okay, so we'll have more to say on that in a couple weeks. Okay, but these, the second and third, okay, the second one, these, you keep multiplying by something bigger than 1, the product is just going to keep getting bigger and bigger. So that limit's infinity, this thing clearly diverges. The third one, the limit equals 1/2. And so sometimes a common error is to see that that limit does not go to infinity and say, okay, it might converge. But remember, the nth term test is that if the nth term doesn't go to 0, the thing doesn't have a chance to converge. So, and if you think about it, if you just keep adding a half plus a half plus a half plus a half, and you just keep on adding a half forever, your sum is going to get really big. It's going to take a while, but eventually it will get really large. Then the last one, okay, this is a definite classic figure on bottom situation. Log does not grow quickly at all. N squared is going to grow much faster than log. So the limit of that is 0. And so this thing might converge. Okay. And then maybe next time we'll learn a technique to see a way that maybe we could actually definitively say what this thing, if this converged or diverged. And, what I was starting to say earlier when I was talking about this unit in general is you see 4 series up there. It's like, which series definitely diverge, which might converge? Well, 4 choices. This goes very well in multiple choice. So you could be faced with 4 of these, and it could say, which of the following series could converge? A, B, C, and D. And you would choose D because it's the only one that has the limit of the terms going to 0. All right, so the first kind of class of series that we're going to look at is the geometric series. And we looked at the geometric series in my pre-cal class, but maybe you had a different pre-cal, or maybe you forgot, and you need a little refresher on the geometric series. Geometric series has terms with a common ratio. We've already looked at a geometric series. Okay. We looked at the 1/2 plus a 4th plus an 8th plus a 16th plus a 32nd. Okay, that's a geometric series because the terms had a common ratio of 1/2. So I'll just write down a couple of examples. Okay, so 2 plus 3 plus 4.5 plus, okay, I can't really think of what the next one would be. Maybe 6 3/4. I'm not sure. I don't want to write the wrong thing down. Okay, so I'll just say it like this. Okay, well, this is the sum from n equals 0 up to infinity, because I've got that dot, 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 indicating this is not going to stop, of, well, I start with 2, and each time I multiply by 1.5. You could write this as the sum from 1 to infinity of 2 times 1.5 to the n minus 1 power, but I would encourage you to write it however you see it. Okay, but this is the type of thing that we do need a little bit of practice on, just kind of writing sums in sigma notation. And here is the next one. This one is one that's definitely going to diverge despite not going to infinity. So let's look at 2 minus 2 plus 2 minus 2 plus 2 minus 2, and so on. Well, if you think about the nth partial sum, the first partial sum is 2, the second partial sum is 0, the third partial sum is 2, the fourth partial sum is 0. So what's happening is the nth partial sum depends on if n is even or odd. If n is odd, the partial sum is 2. If n is even, the partial sum is 0. And as n goes to infinity, there's no limit to that type of function. It just bounces back and forth. It's like this limit of sine of x as x goes to infinity. It doesn't exist. It's not going to infinity, but it still doesn't exist. The limit of these terms is not 0. Therefore, the thing diverges. Because if you think, it's not converging towards one particular number. So I can write this as the sum from n equals 1 up to infinity of 2 times negative 1. Well, you would think maybe to the n, but then you plug in n equals 1 and see, is your first term positive 2? No, it's negative 2. So maybe I'll add 1 here. You could subtract 1 as well. It doesn't really matter. You just need to offset it by 1. Yes, you could also start at 0. So I'm just trying to, impress upon you that there's more than one way to write a series in sigma notation, which is why in a free response setting, it would be very unlikely for you to be asked to cook up your own sigma notation for something. In the Taylor series, it usually kind of falls into place like that. Okay, so I'm going to need to get myself a little more room so I can do another example. So let's look at 18 minus 6 plus 2/3. No, excuse me, I jumped ahead. Plus 2 minus 2/3 plus 2/9 minus the rest. Okay, well, this is definitely a geometric series because each time I'm multiplying by negative 1/3. So that common ratio is negative 1/3. But I think I'd like for you to try to, write down the rest of it in sigma notation. So I'm going to freeze the screen. And remember, what you write might be different from what I write, but it could still be correct, okay? Provided that the first term matches with 18. Okay? And for those of you watching at home, you can just maybe try to think of what you would write down and then just look and see, is it the same as what I wrote? Is it slightly different but equivalent? That's the idea. So I decided to start my series at 1 and use that 18 and then say negative 1/3 to the n minus 1 because I want to start at 18, so I could take negative 1/3 to the 0 power, which would just be multiplying 18 by 1, and that would be a safe place to start. You could start n equals 0 and then take negative 1/3 to the n. You could start at n equals -1 and do 18 times -1/3 to the n plus 1. Not sure why you would want to do that, but, you know, that is an option. And the most important thing about a geometric series is that common ratio. Okay, that's what makes it a geometric series. That's what's going to define whether or not it converges. So I'm going to kind of look at the common ratio, which is always the thing that's getting taken to the nth power, the n plus first power. And so I'll write for this one, the common ratio r equals 1.5. Over here, the common ratio r equals -1. And for the third one, the common ratio r is -1/3. So the relevant fact is that if r is between -1 and 1, meaning greater than -1 and less than +1, then the value of the infinite series is given by the first term multiplied by 1 over 1 minus r. And this is a thing that we did do last year in pre-calc. Okay, we used that formula. I may have even proved the formula for you. I don't really remember. That was a long time ago at this point. So I'm gonna even give you the proof of this. I'm gonna scroll this up a little bit and set up for the proof. Well, I'm gonna start by just saying the infinite sum, S infinity, is going to be given by A plus A multiplied by R. Now I'm presuming we're starting with n equals 0, but either way, A is just the value of the first term. And I write first term rather than A sub 0 or A sub 1 because who knows what the series is going to start at. Maybe the series starts at 5, and if you're stuck with A0 divided by 1 minus R, you could be confused. But if you always remember it's just the first term times 1 over 1 minus R, you're better set up to deal with series that start at different values of n. Okay, so then I'm going to just keep multiplying by R. And I think 4 should probably be enough for you to see the picture. All right, now what I'm going to do is I'm going to take this equation and multiply both sides by R. That's legal, right? And so I'm going to distribute in the R, but I'm actually going to kind of shift over the terms to the right by 1. So it starts with A times R plus AR squared plus A times R to the third, A times R to the 4. I'll have A times R to the 5th and all the rest of them after that. And now what I'm going to do, I'm going to kind of just like label these as, you know, maybe equation 1 and equation 2. And then what I'm going to do is I'm going to ask you to consider what happens when you take equation 1 minus equation 2. Well, I can do that. That's going to be S sub infinity minus R times S sub infinity, given by, okay, and I'm going to subtract down. Okay, A minus 0 is A. AR minus AR, when I subtract, that's 0. AR squared minus AR squared, 0. AR to the third, also 0. All of these things are going to cancel off, right? All of the infinite terms are going to have their kind of their friend down on the lower line to cancel off with. Okay. And so it'll really just be equal to A plus a bunch of zeros, right? Okay. And then what I'm going to do is I'm going to factor out S sub infinity. And I'll be left with a 1 minus R. And then now you start to see where this is going to happen. Okay, this is equal to A. And then the value of the infinite sum is going to be A, and I'm going to divide by 1 minus R. Now, in our case, A was that first term. So that's where I get first term times 1 over 1 minus R. Okay, that's another one where the proof, not super important to what we're doing in this course, but it's right at y'all's level. I've got a little bit of time today, so I figured I might as well show it to you. Okay, so our first example is from the multiple choice packet, and this was a question that was on the 1997 Calculus BC test. And it's, what is the value of 3 halves plus 9/16 plus 27 over 128 plus 81 over 1024 and so on. And so I'm going to look and I'm going to see, well, I multiplied by 3, multiplied by 3, multiplied by 3. And then in the denominator, I multiplied by 8, multiplied by what looks like 8, and then I'm just going to probably take it on faith. It seems like that's probably times 8 as well. It's a geometric series, so. And you can check with the calculator that 1024 divided by 128 is 8. And maybe you just know that because you're better at arithmetic than I am. But you're going to find this by saying, okay, this is going to be equal to the first term times 1 over 1 minus the common ratio. Well, the first term is going to be equal to 3 halves. And then the common ratio is going to be equal to 3 divided by 8. So the value of the sum is 3 halves times 1 over 1 minus 3/8. Well, 1 minus 3/8 is 5/8. And if I have 1 over 5/8, that functionally will flip the fraction. So it'll be times 8 over 5. All right, so that's going to be 24 over 10, which is 2.4. And the answers were in decimals, right, with 1 decimal place? Yeah, I remember this question. And what answer choice is that? Okay, C, yeah. All right, I'm going to have another geometric series for us, or at least a question involving them. Okay, next we have one that I'm pretty sure is some kind of old multiple choice question, but is not in the packet. I must have just missed it when I was flipping through the old release tests that I have. And it's basically asking for, find me the values of x that make this geometric series converge. Now, if you see, a fraction to the nth power, or something that's equivalent to a fraction to the nth power, that's going to be geometric. Okay, so what I'm going to do is I'm going to rewrite this thing as the sum from 0 to infinity of x minus 1 divided by 3 to the nth power. And this is definitely geometric, right? So you're just multiplying by the same thing every time, especially for a given value of x. Okay. Well, I know that in order for a geometric series to converge, the common ratio needs to be between -1 and 1. And that common ratio is x minus 1 divided by 3. So this is one of our old-fashioned, just solve the inequality. So I'm going to multiply all 3 sides by 3. I'm going to add 1 to all 3 sides. And I get -2 to 4. Okay, not including -2, not including 4. The question was, why not including if the ratio is equal to 1, this is not something I really talk about, but if the ratio is equal to 1, you keep adding the same number over and over again. And provided that that number is not 0, that's going to cause your thing to either grow towards infinity or maybe towards negative infinity. Either way, by the nth term test, it will not have a chance to converge. If it's -1, then it's like that 2 minus 2 plus 2 minus 2 series, which did not diverge in the sense that it went to infinity or got bigger and bigger and bigger, more negative, more negative, more negative, but it didn't converge. It failed to converge. Oh, so, okay, it turns out this is number 10 on the multiple choice. Okay, so it was in there. I'm glad to hear that I didn't miss one, because there's so few available that I try to get y'all all the ones I can. All right, and the last thing I'm going to talk about in this video is going to be the telescoping series. And so we're going to consider the series given by the sum from 1 to infinity of 1 over n minus 1 over n plus 1. Now, this is the type of thing that can be put together with a common denominator and ending up being one of those fractions with a factorable denominator that a couple of units ago we integrated by decomposing with partial fractions. Okay? This is very unlikely to show up on the AP exam, but I really like the telescoping series, so here we are and we're doing it, okay? And it's another really good opportunity for us to practice our partial fractions. It wasn't like we had a problem with decomposing with partial fractions in Unit 9, but, you know, in case we needed to be reminded of it, it's always good practice, okay? I'm going to actually write out the terms of this series. Okay, so I'm going to start with 1, so 1 over 1 minus 1 over 2, plus 1 over 2, n is 2, minus 1 over 3. And then when n is 3, this will be 1 over 3 minus 1 over 4. And I'll do one more when n is 4, 1 over 4 minus 1 over 5. And then wouldn't want to forget the dot, dot, dot to indicate that this pattern is going to continue. And what ends up happening is when you have negative a half plus a half, well, that's going to add to 0. And then you have negative third plus a third, negative fourth plus a fourth, negative a fifth. I guarantee you that there's going to be a plus a fifth after that. And so all of these things are collapsing, which is what they call it the telescoping series, right? And the sum is just equal to 1. So this is a telescoping series. All right, and I'm not going to, waste a bunch of time by doing a bunch of examples of telescoping series, but I am going to do one. I'm going to start by, it's like, oh, man, if I just plug in on n, this is going to be, it's not going to have much of a pattern. It's not going to seem like much sense can be made out of it. Instead, what I'll do is I'll break this thing down with partial fractions. Okay, so let's go ahead and do that. So I'm going to say 1 over n plus 2 times n plus 1 is equal to a over n plus 2 plus b over n plus 1. And that indicates to me that 1 would be equal to a times n plus 1 plus b times n plus 2. And then I'm going to just start with maybe n equals negative 2. And I'll get 1 equals negative a, which means a is negative 1. And then if I let n be negative 1, I'll have 1 equals 1b. So b equals 1. So I can write this now as the sum from 1 to infinity of, well, I'll put the negative 1 to the right, so it'll be 1 over n plus 1 minus 1 over n plus 2. And then I will, start with n is 1, so this will be a half minus a third. N equals 2. 1/3 minus 1/4. N equals 3. 1/4 minus 1/5. And I think you all get the picture. I'm going to start adding these terms together. Negative third, positive third. Negative fourth, positive fourth. Negative fifth, well, there will be a positive fifth coming after that. And so this sum is equal to 1/2. I think that's all I got for you on this video.